Okay, so we are talking about vector spaces, and we defined in the last class we defined basis of a vector space, and we have seen that any two. So, suppose V is a vector space over a field F, then the basis means if it is finite dimensional, then the basis is basically the set of vectors alpha 1, alpha 2, alpha n, such that this is a linearly independent set of vector and this span the whole space. Then the V is called, if these two satisfy, then the V is called basis of V is called a basis of this B is called a basis of V. And in the last class we have seen, if we have two bases, then they have same number of vectors. So, any two bases of a vector space is having same number of vectors. So, and that number is called dimension of the vector space. So, that this theorem we proved in the last class. Any two or any basis of a vector space of a finite dimensional vector space. Finite dimensional means we have some finite set of vectors whose can generate this vector space, that is the finite dimensional. Otherwise, if no such vector finite set of vector exists, then we say this is a infinite dimensional vector space. Any basis of finite dimensional vector space V over a field F has same number of element in the number of vectors. Okay. The same number of vectors, and that number is called dimension of the vector space, and this number is called, this is called dimension or rank, this is also called rank of the vector space of V. This is how we define the rank of or dimension of a vector space. So, rank or dimension of a vector space is basically the number of vector in a basis, the cardinality of the basis of the vector space, and every basis has same number of elements. So, that number of vector in a basis, the cardinality of that basis set is called dimension of the vector space. Now, if we consider the null vector, that is a vector which consists, suppose we have a vector space over a field this. Now, we know this 0 vector is a subspace, it is called a null space, and this is the convention. So, this is we denote this n. So, this is the convention, dimension of n is 0. This is the convention we use the dimension of n is 0. So, that means the dimension of a vector space is basically number of element in the basis, and the basis contain all non-zero vector. We will not consider 0 vector, because 0 vector has no contribution in the basis. So, basis consists of all non-zero vectors. So, for that we need to separately define the dimension of this vector space. This is a vector space. This single, we can prove all the properties of the vector space. This singleton set is a vector space. This is a subspace of V. If this is a vector space, and this is this singleton set, this is a subspace, we can prove that subspace of V. Now, the dimension of this is taking to be 0, this is the convention. So, the dimension of null space is 0. So, dimension of a vector space is basically number of element or cardinality of the basis, where B is a basis of V, and dimension of this null space is 0. This is the definition of a dimension of rank of a vector space. Okay, so now we will take some example of some vector space and their dimension. Suppose we consider R 3. So, if our vector space is R 3, this is basically 3 tuples over the field R. Then we know a basis like this standard basis 1 0 0 0 1 0 0 0 1. This is the basis of R 3. So, the cardinality of this set is 3. There are 3 vectors in this basis. So, dimension of this R 3 is 3. Okay. Similarly, R to the power n, if you consider the n tuples set of n tuples vectors, then this has a basis. So, this is the standard basis 0 1 all are zeros. So, there are n element in the basis. So, the size of this is n. So, the dimension of R to the power n is basically n. Okay. So, this is some example of the dimension of this. So, now we will talk about some result on this dimension and the basis. So, this is a theorem. Suppose you have a vector space V over a field F, okay, and suppose its dimension is n. So, that means there exists a basis of n vectors. So, that is the dimension of them. Suppose the dimension of V is n. Okay. Now, this theorem is telling let alpha 1 alpha 2 alpha n be any set of n independent vectors Li vectors of V. Okay. Suppose this we denote by B set. Then the theorem is telling then B must be B is a basis of V. So, that means, if we know the dimension of this vector space is V, then if we have any set of vectors of n vector alpha 1 alpha 2, any collection of such n vector will form a basis. So, that is the claim. Okay. So, any collection of n linearly independent vector will form a basis. So, for basis we need 2 properties, one is linearly independent, that is already there, B is linearly independent, and the second property is it should span the set. So, that means, given an element from V, V say beta, we should able to write this beta as a linear combination of alpha. That is the meaning of spanning the set V. So, how to show that? How to show this beta can be written as the linear combination of alphas. So, let us consider this set alpha 1 alpha 2 alpha n beta. Okay. Now, suppose there are 2 cases, case 1 that beta is none of these alphas. Okay, we are taking beta from outside alphas. Now, then we know if the dimension of this is n, then there are at most n number of linearly independent set of vector. So, that means this set must be linearly dependent. Because it having n plus 1 vector and our dimension is n. So, that is not possible. So, if it is linearly dependent, so that means there exists some C 1 C 2 C n, C 1 alpha 1 plus C 2 alpha 2 C n alpha n plus some C beta is equal to 0, 0 vector such that not all of these C i's are 0. That is the meaning of linearly dependent. So, not all C i's are basically 0. Now, we claim that C cannot be 0, this coefficient, because if C is 0, then then we have the expression, if C is 0, this implies C 1 alpha 1, C n alpha n is 0. Now, alpha 1, alpha 2, alpha n are linearly independent set of vectors. So, this implies all C i's must be 0 for all I equal to 1 to n. So, this implies all these coefficients are 0 including C is 0. So, that is that will imply this is the linearly independent set of vector, but which is not possible, because this contain the number of element is more than the number of element in a basis, because basis is having dimension is n. So, basis contain n number of vector. So, that means this C I is not equal to 0. I see if C is not equal to 0, then we can write this as C beta is equal to minus C 1 alpha 1 minus C 2 alpha 2 like this. This is small c, C n alpha n. Now, if C not equal to 0 scalar, then C has a inverse C inverse. So, we multiply these both side by C inverse. So, beta can be written as minus C 1 C inverse alpha 1 minus C 2 C inverse alpha 2 like this, minus C n C inverse alpha n. So, this we can say some d 1 alpha 1 dot 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 plus d n alpha n. So, this is basically our d 1 d 2 like this. So, these are basically linear combination of these vectors. So, if we denote this by say so beta can be written as linear combination of these vectors. So, if you take any vectors from V, so this is our V set. If you take a vector from V, so V can be written as the linear combination of this, where beta is not equal to sum of the alpha. So, this implies that V is a subset of L of B. B is the collection of all alphas. Okay. And also, if B is equal to sum of the alpha I, then obviously B can be written as the linear combination of this. And also, B is a subset of this, B is a subset of V. So, that means L of B must be subset of V. So, these two will give us. So, that means B is generating the vector space. So, B is a span of this. So, that means B is a basis of this. So, B is a basis of V, because B is already linearly independent set and any vector from V can be written as linear combination of B's. So, this will give us the result that B is a basis of B. So, any set of n linearly independent vector will give us a basis if the dimension of the vector space is n. Okay. So, this is very interesting result. So, if we can get any, suppose we are talking about R 3, then dimension is 3. So, if we can construct any set of linearly independent vector of dimension of size 3, then this will form a basis. So, that is the that kind of example one can construct on this. Okay. So, now we will try to do some examples on this. Suppose we want to, the question is, suppose we want to find, this is the example, we want to find a basis of the vector space R 3 that contained certain vectors. What are those? We want a basis from R 3 that contain these two vector. So, how to solve this type of problem? Here we'll just use the replacement method which we know. Okay, so how to solve this type of problem? Now, we know some bases on R 3, they are standard bases, say this is a standard basis of R 3 B 1 0 0 0 1 0 0 0 1. This is a epsilon 1, epsilon 2, epsilon 3, say these are called standard bases. Okay. Now, we want to write this as a linear combination of this. So, this is a alpha vector, this is a beta vector. Now, alpha can be written as in which way? Alpha can be written as 1 epsilon 1 plus 2 epsilon 2 plus 0 epsilon 3. We can easily check that. Now, this is non-zero. Now, we know the replacement theorem of the basis. Now, if any vector can be written as linear combination of this of the basis element, then any vector can be written as, now we can replace the non-zero vector whose coefficient is non-zero here. So, that means this is non-zero. So, instead of this we can write alpha. So, that means B 1 if we write alpha. So, we are replacing epsilon 1 by alpha. Epsilon 2, epsilon 3 is also a basis, of R 3. This is because of the replacement theorem. Okay. Now, since it is a basis of R 3, we should be able to write beta in terms of this. So, that we are going to, we want to try that. So, the beta will be written as, we can easily check that, alpha plus epsilon 2 plus epsilon 3. Okay. Now, again epsilon, this is a linear combination of these vectors in a basis. Now, this has one non-zero term. So, we can take replace by again replacement theorem, we can write, we can replace epsilon 2 by beta. So, this is also a basis, this is a basis of R 3. So, basically we are using the replacement theorem, we know replacement theorem on basis, which we have discussed in the previous lecture. So, that is it. So, this is the basis we are looking for. So, this basis contain alpha beta. So, this is the way we can generate a basis with some vector. Okay. So, we will take some more example on the basis. Suppose on R 3 again, we want to see whether this will form a basis or not. So, 2 1 1, this is another basis. Okay. So, to check this, so this is alpha 1, alpha 2, alpha 3. So, we can just check this whether this is a form a basis. So, for that we need to show that this is Li. This is linearly independent set of vector. So, that means we need to show this, we need to take alpha 1 linear combination of this to be 0 vector 0 0 0, and this we need to show this is only possible if all the coefficients are 0. This we can easily verify that. Again we can take a vector from this a b c from R 3, any vector, then we can easily verify that a b c can be written as some linear combination of this vector. So, this is exercise we can take. Okay. So, again you can find the d1, d2, d3 in terms of a b c. This I am leaving you for exercise. Okay. So, this will form a basis. Now, another example on the subspace of R 3, suppose we are taking the V is equal to R 3. Now, we are considering the subspace on R 3, say A B C belongs to R 3 such that A plus B plus C is equal to 0. We can easily verify this is a subspace. Now, we are interested to get the basis of this subspace or dimension of this subspace. Now, we can take a W from this W. So, W will be say A B C. Okay. Now, we know that A plus B plus C is 0. So, C can be written as minus A minus B. So, this is basically A into 1 0 minus 1 plus B into 0 1 minus 1, and this is for any ABC. So, we can write any vector W as a linear combination of these two vectors, and also we can check these two vectors is linearly independent set of vectors. So, that means 0 1 minus 1 and 0 1 1 0 minus 1, this is a basis of W. So, there are two vectors in the basis. So, dimension of W is basically 2. So, dimension of this W is 2. So, this is one of the example of this. Now, we will discuss one theorem which is called extension theorem. So, that is telling us, suppose we have a linearly independent set of vector. Now, it is either will form a basis or we can extend it to get a basis. Okay. So, let us write that. So, this is what is called extension theorem. Extension theorem. It is telling us, the statement is a linearly independent set of vectors of a finite dimensional vector space over a field F is either a basis or it can be extended to a basis. That means, we can add some more vector to have a basis, or it can be extended to a basis of V. So, idea is, suppose we have a vector space V. Now, suppose we take a set of vectors alpha 1, alpha 2, alpha r. This is a linearly independent set of vectors. This is say S. Okay. Now, now this is when it will be basis, if L of S equal to V. If L of S equal to V, then we know this is linearly independent set. So, by the property definition of basis, we can say S is a basis. Now, suppose L of S is not equal to V, we know L of S is a subset of V. So, if it is a proper subset, so that means, if V intersection L of S, or if say V minus L of S, if this is not null. So, that means, if there exists some vector which is not a linear space. So, this is our V and this is say L of S. So, this is generating by the vector alpha and alpha to alpha. So, suppose this is not covering whole space. Now, say suppose there are some element which is outside this. So, now we have to get some more element in the basis to cover whole. So, what is the idea? Idea is to get some more element from here. So, V minus L of S is not empty. So, we take a beta from here. So, beta belongs to V minus L of S. Now, we add this beta with, or beta 1 we can say, alpha r beta 1. This is our S1. Okay. We have S set alpha and alpha to alpha r. Now, we from S we get a S1. by adding a vector which is not a linear span of this S, which is outside this beta 1. Now, we can show this is again this, we can show this. This is again linearly independent set of vectors, and again if this S is covering the whole space, then it is a basis. Otherwise, again we will choose a beta 2 from this V minus L of S 1, and we add this beta 2 here, S 2 alpha beta 1 beta 2 like this. So, this way we extend this until we are not getting the set which can cover whole space. So, this is called extension theorem. So, we will take a quick example on this. So, idea is very simple, we are keep on adding the element which cannot be written as the linear combination of this set. So, if we add that vector, then slowly we will get this. So, just a quick example on the extension. Suppose we are considering R 4. Now, suppose we take two vectors, say standard vector for simplicity, or say R 3, sorry, it will be easier. If we have two vector, now this is a linearly independent set of vector, we can easily verify that. Now, this is not covering the whole space, because it is only covering the space like this. Okay. So, now if we choose a vector, so this is our S, this is our L of S. So, if we choose a vector, this is not empty. So, we choose a vector from here, any vector, say from this space 0 0 or any vector which is having some coordinate over here, say 0, say 1, 0 0, say 2 or 1, say if we are talking about standard vector, if you want to, or say 2. Okay. This is our beta. Now, if we add this beta with this, then we can check this is a linearly independent set of vector. So, and it has three number of 3 vector and dimension of this is 3. So, this is a basis. Also, we can verify that L of S is basically S 1, L of S 1 is basically V R 3. Anyway, this is an example of this thing. Okay, so, now we will define what do we mean by coordinate of a vector. Okay, so, suppose, so this is a theorem we can say. Suppose you have a vector space over a field F, and this is finite dimensional vector space, and suppose you have a basis. So, this theorem is telling this B is a basis of a finite dimensional vector space over a field F, if and only if every element of V has unique representation as a linear combination of B. So, as a linear, we know that if B is a basis, then every vector should be written as a linear combination of the alphas, linear combination of the vector from B. Okay, so, how to prove this? Now, this representation must be unique. So, that is important, and that uniqueness will give us a what is called coordinate. Okay. Now, how to prove this? Now, to prove this there are two parts, if and only part. Suppose B is a basis, then we have to show this representation is a unique. Now, if you take a vector beta from V, so this if this is a basis, then beta will be written as some C 1 alpha 1 plus C 2 alpha 2 plus C n alpha n. Okay. Now, suppose this is not unique, suppose there is another linear combination of this. Suppose B can be written as some d1 alpha 1 plus dn alpha n. Now, if you subtract this, we will get what? We will get C1 minus d1 alpha 1 dot 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 Cn minus dn alpha n is equal to 0 vector. But these alpha is our basis, so they are linearly independent. So, that means Ci equal to di. So, that is the uniqueness. So, that means any vector can be written as unique combination of this, and the reverse also we can, conversely also we can prove this. If we can written any vector as a linear combination a unique way, then this will form a basis. Okay. Now, that is the telling us the definition of coordinate of a vector based on the basis. So, this we define coordinate of a vector with respect to a basis of obviously. So, that means if we have a basis V of a vector space say V f over a field f, if B is a basis, then we have seen that any vector from V can be written as unique linear combination of this some C 2 alpha 2 C n alpha n. Okay. Now, this is a unique representation, and if we, this is a ordered basis. Ordered basis means we are not changing the ordering of this element. If you change the ordering of this element, then the C 2 will come here like this. So, we are taking a ordered basis. We are fixing the ordering of this element, that is the sense. Then this C 1, C 2, C n are called coordinate. Coordinate of beta with respect to the ordered basis B, with respect to the, and this is the unique representation. So, this coordinate is unique. So, this is the definition of coordinate of a basis. Now, we will take a quick example of the coordinate. Okay, suppose we are at R3. Now, say we want to find the, we have a say basis from R3, say B, we can take any basis. So, say we are taking this basis 1 1 0 1 0 0. One can verify this is a basis. Okay. Now, we have a say beta. So, this is alpha 1, alpha 2, alpha 3. So, this ordering is given, we fix the ordering, that is why it is called ordered basis. We have a B where we are not changing this alpha's position, beta's position, this is the ordered basis, say that sense. Now, we take a element 1 3 1. Now, we want to represent this. So, this is a vector in R3. So, this should be written as a linear combination of this basis element. So, C 1 alpha 1 plus C 2 alpha 2 plus C 3 alpha 3. So, we can easily check that C 1 will be 1 alpha 1, C 2 will be 2 alpha 2 plus C 3 will be minus 2 alpha 3. We can check this. So, that means this beta coordinate of this beta with respect to this ordered basis means we are not, again I am telling, we are not changing the position of this. If we change the position of this, if we take alpha 2 here, then C 2 will come here. So, we are not changing, we are fixing the position of this, that sense it is an ordered basis. So, then the coordinate of this is basically 1 2 minus 2. This is the coordinate of this vector, this with respect to this ordered basis B. So, this is the example of a coordinate of a vector. Thank you. Thank you.